Hi everyone, welcome to your Test 1 review material. Now in the first module I included a document that had the energies, half-lives, and decay method for common radioactive isotopes. Unfortunately, you're just going to have to memorize this material. It's going to be useful in this class and in many of the other courses that you take during the program. The first thing that we're going to talk about is the Bohr atomic model. Now when you think about the Bohr atomic model, you're going to be talking mainly about the nucleus, which is the protons and the neutrons, and the electron shells. So when you think about the nucleus, it's composed of the nucleons, so that's very positively charged protons, and then neutrally charged neutrons. Now the nucleus combined together, the protons and the neutrons, is where you're going to be getting the mass of the atom. Nucleons in the nucleus are bound together by strong nuclear forces that are considerably stronger than the electrostatic forces of repulsion between the protons, because if you think about it, all of those protons with those positive charges should be repelling one another, so it takes something that's even greater than that repelling force to hold that nucleus together, to prevent the nucleus from just breaking apart into free-floating protons and neutrons. So the positive charge of the nucleus is due to the number of protons inside. The neutrons add mass, but they don't actually add any charge. So that nuclear binding energy is actually the energy required to separate a nucleus into the individual nucleons. Restated, it's the amount of energy released when the nucleus is assembled from protons and neutrons, and again that comes from the mass. Now again, the other part of the Bohr atomic model that we generally talk about would be the electrons, and I've heard that referred to as the electron shells, the electron clouds. All of those things would be considered appropriate, but I like to think about the electrons as being housed in very discrete orbits or shells around the nucleus. Now that's not exactly true, but that's the easiest way to think about it. So all of those negatively charged electrons are going to be very, very, very attracted to that positively charged nucleus. And the more protons in the nucleus, the more strong that attraction is going to be. And these electrons are housed in these shells. Usually they're designated starting with the K shell being the closest to the nucleus and then working out from there, K, L, M, N, O, P, Q shells. And then there's a specific number of electrons that can actually be contained within those shells. And I'm not going to review that with you. That's kind of a basic chemistry thing. But of course the K shell electrons total number could be 2, L, the number of electrons would be 8, and so on and so forth. Now these electrons again are attracted to the nucleus by that electrostatic force, or the Coulomb's force. Now again, the electrons are attracted to that positively charged nucleus by these electrostatic forces. So there's going to be energy required to overcome this electrostatic force in order to remove an electron from its shell. The energy required to liberate one of those electrons from that shell is called the electron binding energy. The binding energy between the electron and the nucleus, really it depends on the number of, again, protons in the nucleus and the distance separating the shell from the nucleus itself. So a K shell electron is going to be require much more energy to remove because it's closer to the nucleus. That positive and negative charge is going to be very much attracting each other. So it's going to require a lot more energy to liberate a K shell electron than it would from like an M or an N shell electron. So again, the binding energy of an electron in the K shell is going to be much greater than that of the binding energy electron in an L or an M shell. So just as I think this is kind of confusing to some students, so just to kind of try to make this a little bit easier for you to understand. The binding energy itself is not an energy that's possessed by the electron, but it's the amount of energy required to remove that electron in order to free it from the attraction of that nucleus. And if you think about it, binding energy is considered like a negative energy. So the binding energy of a K-shell electron to the atom is greater than the binding energy of the L-shell. But the K-shell electrons themselves actually possess less energy than the L-shell electrons because they have more negative energy. So the L-shell electrons are more energetic and they don't need as much energy as an electron in the K-shell in order to break free from that nucleus. Let's talk a little bit about atomic nomenclature. So in this general representation, the letter X would be the element, the specific element that you're talking about. The number of protons in the nucleus is generally referred to as the atomic number, and it's symbolized by the letter Z. The number of protons and neutrons in the nucleus of an element is called the mass number, and that's usually designated by the letter A. And I know that electrons do have a tiny, tiny amount of mass, but generally speaking, whenever you're talking about the mass of an element, you're referring to the protons and the neutrons. And of course, N would then designate the number of neutrons. So how do the elements actually relate to one another as far as the designation of isotopes, isotones, isobars, and isomers? Atoms of the same element can actually have different masses. So the element is denoted by the number of protons, okay? But you can have a different number of neutrons, and that would actually change your mass, right? Because your mass is the combination of the number of protons and the number of neutrons. So atoms of the same element with the nuclei containing the same number of protons but a different number of neutrons are actually called isotopes. Now these isotopes are actually going to have the same chemical properties because the chemical properties of an element are dependent upon the configuration of the orbital electrons. But the nuclear properties are going to be very, very different. Okay, so again, the isotopes are atoms of the same element having the same chemical properties, same atomic number Z, but different mass number A. I'm sorry, I clicked over before I was quite finished talking about that slide. So common isotopes are represented by like carbon-11, carbon-12, and carbon-14. Isotones refer to nuclides that have the same number of neutrons but possess different atomic numbers, different mass numbers, and of course different chemical properties. Isobars have the same mass number A but different atomic numbers and different chemical properties. Sorry about that long pause. I was trying to get a drink. And then you have isomers. And isomers occur because certain nuclides like technetium-99, the nucleus can actually have two different energy states. So these two forms of technetium-99 are called isomers. The two isomers of Tech-99 have the same atomic number and mass number, but they exist in different energy states. And that brings us to the chart of nuclides. So certain combinations of protons and neutrons produce stable, non-radioactive nuclides, but then others don't. Some have too many neutrons or too many protons to be stable. Some even have too many neutrons and too many protons to be stable. But the stable nuclides occupy, if you look at the chart, kind of this, it's represented as a narrow band. It's the black boxes that kind of go right down the middle of the blue and the orange swath there, and those are stable nuclides. Now technically, most elements have several stable isotopes. So the stability belt, that's what that kind of black swath is. It's the line of stability. It's actually a broad band rather than the narrow one that's represented. But you know, this was the representation that I found, and it's honestly, it's kind of how it's denoted in most textbooks. So nuclides lying outside of the stability belt are unstable, and they attempt to move towards the stability belt by changing the relative proportion of neutrons and protons within that nucleus. Any excess energy in the new nucleus is carried away by emitting as particles and or electromagnetic radiation. So the process by which a nucleus transforms itself from one form to another is radioactive decay. So isotopes that have too many neutrons or protons, you know, they undergo this radioactive decay. Typically, if the nuclide has too many neutrons to be stable, it's going to undergo beta decay. Nuclides that have too many protons to be stable typically undergo positron decay or electron capture. And nuclides with too many protons and too many neutrons to become stable undergo alpha decay. So if you look at the chart that I included on here, the blue pixels are the nuclides that undergo beta decay. So beta decay is usually denoted by the beta minus. So that's typically what's called beta decay. And then underneath of the line of stability, so underneath of the black line, so to speak, are the orange pixels. And those nuclides are the ones that have too many protons. So they have too many protons to be stable, so they undergo that beta decay and or the electron capture. Now up towards the top, so is the number of neutrons and the number of protons is you have too many neutrons and too many protons denoted by the little yellow pixels. Those are the ones that undergo alpha decay. I think it was in your first PowerPoint I included what a decay scheme is, and typically whenever a nuclide undergoes alpha decay, it's going to lose 2 protons, so the Z number is going to be lower because the atomic number is decreased. For beta decay, a neutron is converted into a proton, so the daughter is 1 unit higher than the parent. So it's actually to the right if you're thinking about it as on a chart of nuclides or on a chart of elements, because the atomic number increases. So for positron decay, the proton is converted to a neutron and of course a positron and a neutrino, so the atomic number decreases by 1. And in a gamma decay, it's just a change of, there is no change in the atomic number. So again, this is just kind of a a representation of what a decay scheme would look like. And I didn't include any of the examples that were from your first PowerPoint. You'll have to go back and review those. But if you're wondering why, whenever you're looking at a decay scheme, one element will be to the left versus straight down or to the right, and it's essentially just talking about the number of protons that are lost or a shift that occurs in the protons or the neutrons. Now when we talk about radiation, we're pretty much going to be talking about ionizing radiation. So there's different types. There's the non-ionizing and ionizing. Non-ionizing would be like light, radio, and microwaves. Ionizing would be what we called primary charged particles, and those are the alpha and beta particles. And then photons, such as gamma rays. In the ionizing radiation are produced by those unstable atoms, so those radionuclides that are going to decay as they're trying to become more, or as they're trying to move closer to that line of stability. When we talk about types of radiation, generally you talk about primary, secondary, and electromagnetic radiation. Now primary radiation originates from the target or the source. So the beam of photons exit a tube before interacting with the patient's body. Secondary radiation is radiation produced when the photons interact with the body. So it interacts with matter, essentially, and the photon travels in a different direction. So that's caused by attenuation, and that's the process of the body matter absorbing the primary radiation. And then there's electromagnetic, which is radiation consisting of electric and magnetic waves that travel at the speed of light. And examples of electromagnetic radiation include X-rays, gamma photons, microwaves, visible light, infrared, ultraviolet radiations. All of those fall into that electromagnetic spectrum of radiation. And remember, electromagnetic radiation has no mass and it does not carry an electric charge. Now, electromagnetic radiation has three primary characteristics: wavelength, frequency, and velocity. And I'm not going to go into really any detail on that, but it's just worth mentioning that, again, electromagnetic radiation doesn't have any mass and it doesn't have any kind of electric charge associated with it. And certain characteristics of EMR are best described by propagating waves. And other properties are better explained by considering it a charged particle. And again, charged particle would be like an alpha or a beta. So electromagnetic radiation is quite a bit different. It actually it's not made up of waves and particles, but it has this kind of dual nature where it behaves sometimes like a particle and sometimes like a wave at other times. So like, for example, the propagation of electromagnetic radiation, you can describe it more of like in terms of waves. And whenever you're talking about the mechanism of interaction between like an X-ray and a gamma ray and different types of matter, that's best explained by treating the radiation as a particle, even though it's really a photon, or a photon you can think of as a tiny packet of energy, because they don't have electrical charge. And so they don't interact with matter through any kind of electrical forces like other charged particles would. So when I spoke about the electromagnetic radiation, I mentioned both gamma rays and X-rays are different types of EMR. So what's really the difference between a gamma ray and an X-ray? They have like the same amount of energy associated with them, but the difference is where those types of radiation are generated. So gamma rays are generated in the nucleus as a result of a transition from an excited nuclear state to one of a lower energy. X-rays are generated by the electrons in one of two ways. As a characteristic X-ray, and that's again when you're talking about those different electron energy shells. One of the outer shell electrons fills a vacancy left by an inner shell electron being ejected from the atom. And that produces an X-ray with a very specific energy. It's characteristic of that nuclide. Okay, and then the other types of X-rays that you're going to hear us talk about would be our what's referred to as Bremsstrahlung, or braking radiation. And what that is it's a high-speed free electron that can interact with matter by slowing down as it travels near the nucleus. The amount of energy released is going to depend on how close the electron gets to the nucleus, and it produces this very broad spectrum of photon energies. But again, Bremsstrahlung radiation is just referred to as braking radiation. So now we're going to spend a little bit of time talking about radioactive decay mechanisms, and the first one that we're going to talk about is alpha decay. And these isotopes that undergo alpha decay are just too heavy, so they have too many neutrons and too many protons to be stable. So in order to reach that stability line, they're going to emit protons and neutrons. So an alpha particle is actually just a helium nucleus. So it consists of 2 protons and 2 neutrons. The radionuclide, after emitting an alpha particle, has the atomic number Z that's going to be reduced by 2, and the neutron number N is also going to be reduced by 2. So that means that the mass number, and remember the mass number is the number of protons and neutrons, is going to be reduced by a total of 4. Now, in order for a nucleus to eject such a large particle, because that is a large particle, the nucleus is going to have to be relatively large, okay? So that means that it's going to have at least an atomic number of 83 or higher, but usually it's even greater than that. So radium is a typical alpha emitter. So radium-226 decays to radon-222, and as it does, it emits that helium atom. So alpha particles, although they're emitted with a lot of energy, they can be stopped in just a few thousandths of a centimeter in tissue. So even in air, so not even in tissue, but even in air, an alpha particle can only travel 2 to 6 centimeters. So it has a high amount of energy, but it's not going to travel very far. So in the body, it might actually only traverse 1 or 2 cells. So if you're talking about like how to block the passage of those alpha particles, even something like a thick sheet of paper is all that's necessary to completely block the alpha particle. So alpha emitters aren't used in nuclear medicine imaging because they're internally deposited particles and they can't exit the patient to be detected by the radiation instruments. But alpha emitters such as radium-223, that's the common, the brand name Xofigo, they're useful for treatment in that metastatic bone pain caused from castration-resistant prostate cancer, because they only travel a very short length. So it allows all of that energy, all of those discrete energies of 4 to 8 MeV, is going to be deposited primarily into that bone cortex, and it's going to have relatively little dose going to the bone marrow. So again, alpha emitters aren't really useful for imaging purposes, but they are incredibly useful for therapeutic purposes. When you think about a therapy dose, what you want is a high amount of energy that's deposited very focally. So you don't want something that's going to go all throughout the body, potentially damaging other organs. You want it to just go to the area of interest. So we're going to move on to beta decay, and I'll oftentimes refer to this as beta minus decay. So nuclides that undergo beta decay have too many neutrons in order to be stable. So during this type of decay, a neutron is converted to a proton, and an electron and an antineutrino are emitted. So the mass number is going to stay the same, and the atomic number, the Z number, is going to increase by 1. Any excess energy in the nucleus after beta decay is emitted as gamma rays, internal conversion electrons, and other associated radiation. Now, the beta particle ejected from the nucleus is identical in every respect to that of an ordinary electron with the exception of its origin. The nucleus after the beta decay has one additional proton, but one less neutron than the parent. So again, that means that the beta decay is going to result in a daughter nuclide with the atomic number Z increased by 1 and the mass number A unchanged. So if you think about it, beta decay is an example of an isobaric transition. Remember an isobar? It's an example of an isobaric transition because the parent and the daughter are isobars of each other because they have the same mass number. Now, beta particles are about 100 times more penetrating than alpha particles, and they can be stopped by things like wood or an aluminum plate or sheet, and they have a kinetic energy of a 0 to 2 MeV range. Let me trying to think of some of the beta emitters that we utilize in nuclear medicine. I-131 is a beta emitter. Now, we don't use that very frequently as far as imaging, but we do use it for therapy, for like thyroid cancer therapy. One of the things that's mentioned here, and we don't really talk about that much, or we haven't really spoken about, is an internal conversion electron. So again, that line that says any excess energy in the nucleus after the beta decay is emitted as a gamma ray, and internal conversion electrons or other associated radiations. So what happens during this is, again, a neutron is converted into a proton, and an electron is going to be emitted. So if you're talking about an internal conversion electron, an internal conversion electron is not the same as a gamma photon or a gamma ray. So in an internal conversion, no gamma photon is going to be emitted. Instead, it's this excess energy in the nucleus is transferred to an electron that happens to wander into the nucleus and liberates it from the atom basically as a high energy free electron. So it's just an electron that shoots out of there. The energy of an internal conversion electron equals that of the gamma photon that would have been emitted from the nucleus, of course, minus the binding energy of the electron. So internal conversion electrons have very specific energies instead of having a continuous spectrum of energies like a beta particle. So positron decay is another type of beta decay, so to speak. But these radionuclides that decay by positron decay, they have way too many protons and too few of neutrons. So the proton-rich but neutron-poor nuclides have an NP ratio that's too low for stability. So what they're going to do is convert a proton into a neutron, and they're going to emit a positron. After the positron emission, the atomic number Z of the daughter nucleus is decreased by 1, and the neutron number N is going to be increased by 1. The mass number A of the parent and the daughter nuclei is the same because the sum of the protons and the neutrons is going to remain the same. Now these nuclides that undergo positron decay, in addition to just having the too many protons with too few of the neutrons. So again, the low N to Z ratio or the N to P ratio. They're also going to have at least a 1.02 MeV of excess energy. So an energy in excess of 1.02 MeV is carried away from the positron and neutrino as kinetic energy. So just like beta decay, the released energy is going to be shared between the positron and the neutrino. Once it's ejected from the nucleus, the positron quickly loses its energy by collisions with other electrons in the environment. When the positron has lost nearly all of its kinetic energy and almost comes to rest, it's going to collide with an ordinary electron, and the positron and electron are mutually going to annihilate each other. So the rest masses are going to be converted into energy, and there's going to be two 511 keV or 0.511 MeV annihilation photons that are going to travel in completely opposite directions. So, I'm sorry, I clicked over on this slide before I was quite finished with the other one. So just for positron emitters, that's the basis of PET imaging. So PET refers to positron emission tomography. So another way that isotopes that have way too many protons to decay is going to be electron capture. Now, as I stated before, one of the requirements to undergo positron decay is that the nuclide is going to have to possess at least a 1.02 MeV energy in the nucleus. Okay, so what about all of the nuclides with a low neutron to proton ratio that don't possess that 1.02 MeV energy in the nucleus? They still have to undergo some sort of decay in order to reach that line of stability, right? So they're going to undergo electron capture. So in an electron capture, an electron is going to wander into the nucleus and it's going to get captured by a proton. That proton, upon pulling in that electron, is going to turn into a neutron. Okay, so you can think of that as the proton's positive energy being canceled out by the electron's negative energy, and it's going to create a neutron. Usually that would also be like a K or an L shell electron that it's going to capture. And then it would be denoted as like a K shell capture or an L shell capture or something like that. But the net effect of that electron capture is the same as a proton emission. So the atomic number is going to be decreased by 1, creating a different element, but the mass is going to remain unchanged. So what else is given off with an electron capture? You're going to have that characteristic X-ray that's going to be emitted and an Auger electron due to that vacancy that appears in the orbital. So remember, as an electron moves from a higher energy orbital into a lower energy orbital, there's going to be a net energy change equal to the difference between the two orbitals' energy levels. So it's going to either be, again, that characteristic X-ray or the Auger electron. So the characteristic X-ray is going to be a photon with a kinetic energy equal to that energy difference. And again, that X-ray is characteristic of the element involved because the orbital energy separations are specific to each element. An Auger electron is a little bit different. So if an electron, following the electron going from an outer shell to an inner shell vacancy, again, you can have that emission of the characteristic X-ray, but you can also have the emission of an Auger electron. So instead of I'm sorry guys, I don't know why, but I just totally lost my train of thought. So let me just kind of start it over. So after an electron coming from an outer shell to fill the vacancy left in the inner shell, the atom's going to be unstable because the excess energy brought into the inner shell. So instead of releasing the excess energy as a characteristic X-ray, the atom can also transfer the excess energy to another orbital electron and thereby ejecting it from the atom. So when that occurs, there's not going to be a characteristic X-ray emission. Instead, it's going to be a very monoenergetic electron, which is called the Auger electron. And that electron that's ejected from the atom, the Auger electron, is going to carry away the excess energy of the excited atom. So again, with electron capture, you're going to have either a characteristic X-rays that are emitted, or you're going to have Auger electrons that are emitted that's going to carry away that excess energy. And a lot of times we don't really talk about characteristic X-rays as having like a significant impact in nuclear medicine imaging, but it actually does. So one of our radioactive isotopes, we don't use it very frequently anymore. It used to be used for a lot of different cardiac imaging, but now it's used primarily for like viability, is thallium-201. And thallium-201 decays by electron capture. So there's a broad peak of energies from like 68 to 82 keV, and that's made up of these characteristic X-rays of the daughter Hg201. Now, if you're, we haven't really gone into this, but as far as imaging purposes go, the counts that we acquire in myocardial perfusion imaging with thallium-201, most of those counts are actually the low energy X-ray photons, just because of their abundance. The gamma rays that are emitted from the decay are actually relatively small compared to the amount of characteristic X-rays that are emitted following the electron capture of that thallium-201. Okay, and lastly, we're going to talk about gamma decay. So with gamma decay, there's going to be no change in the atomic number, neutron number, or mass number in the nucleus after a gamma emission. So every gamma emission is going to be preceded either by electron capture, alpha decay, beta decay, or positron emission. No radionuclides actually decay purely by gamma emission alone. Okay, so there's no pure gamma emitters. So even like technetium-99 M to technetium-99, the parent nuclei technetium-99 M was preceded by the beta decay of moly-99. When gammas are emitted, they have a very discrete energy. But remember, a gamma ray, which is a photon, they're emitted, by that excited nucleus. But remember, they cannot be distinguished from photons of the same energy from a different source, so like those X-rays. One of the things to remember about gamma decay is it travels significantly farther than alpha or beta decay. So remember, alpha decay can be kind of, it doesn't travel very far, even in air, but it doesn't travel very far and can be stopped by like a thick sheet of paper or tissue. Beta, which has a little bit less energy than an alpha emitter, is going to travel a little bit farther but can be stopped by something like aluminum. A gamma, which has less energy than alpha and beta, is going to be able to travel significantly farther, and it can keep going and going and going until it encounters something like lead. Okay, so we're going to talk about interactions of radiation with matter. So when radiation strikes matter, both the nature of the radiation and the composition of the matter are going to affect what happens. Okay, so it all kind of begins with the transfer of the radiation energy to the atoms and molecules heating the matter and even modifying the structure, so to speak. If all of the energy of the bombarding particle, which again the particles would be the alphas and betas, or the photons, so the gammas, is transferred, the radiation will appear to have stopped within the irradiated matter. But if the energy is not completely deposited in the matter, then the remaining energy is going to emerge through the matter, kind of continuing on, so to speak. So as they pass through matter, photons interact with the atoms, and that type of interaction is a function of the energy of the photon, so how energetic is that photon, and the atomic number of the elements composing the matter. For right now, we're going to focus on gamma radiation. So whenever in Nuke Med we talk about gamma radiation, typically the energies would be between 50 and 550 keV. So for that, the predominant type of interaction is going to be what's called Compton scattering. But then you also have the photoelectric is the dominant type of interaction in materials with a really high atomic number, such as lead. And then you also have pair production, which is, it only occurs in photon energies that have greater than 1.02 MeV or 1020 keV. So it's not really important for clinical nuclear medicine. Primarily, you're going to be focusing on Compton scattering and the photoelectric effect, but those are the three main ways that gamma radiation interacts with matter. And you'll also notice that the Compton scattering or the Compton interaction typically occurs with the outer electron shells. The photoelectric is going to occur within the inner shells, and the pair production occurs within that nuclear field. So on the test, you'll kind of want to know the difference. I think I have a few questions about which one would predominate depending upon the energy that would be associated or where it would occur. So if I said what type of gamma radiation is most common with inner shell electrons, you would want to select like photoelectric. Let me go back for just a second, guys, because I don't know if I mentioned this. I'm sure it was mentioned in your previous PowerPoints, but it hasn't been mentioned so far in this PowerPoint. So let me just go back for just a second as far as talking about interaction of radiation with matter. So the types of interactions that occur between the photons and the charged particles, again, they change depending upon the energies associated with it and the elements that are associated with it. But radionuclide imaging and radioactivity counting depends on that radiation interacting with the detector material to create these ions. So what is that? Ionization is the process in which the radiation transmits energy to liberate electrons from the atoms along its path. So it's the amount of energy required to, knock those electrons out. It's that energy that occurs whenever the energy is liberated with these electrons. The mechanisms of interaction of particulate radiation, so remember when you're talking about particulate, so charged particles, that's like alpha and beta particles. They're quite different than those of the photons associated with gamma radiation. But even for the photons, the mode of interaction depends on the photon energy again and the atomic number of the material in their path. So for gamma radiation, Compton scattering or Compton interactions are the most common type of interaction of materials, again, with a low atomic number, so a low Z, so like human tissue. So Compton interactions involve a photon colliding with like a loosely held outer shell electron of an atom. So remember, the farther away from the nucleus you go, the less hold that nucleus is going to have on those outer shell electrons. So the less electron binding energy there's going to be. So they're going to be kind of loosely held to that atom. Now the outer shell electron is treated like it's a free electron in Compton interactions because of the binding energy is much lower than that of the incident photon. Okay, so an incident photon with a really high energy is going to free a valence shell, so valence being like the outer shell electron of an atom, and it's going to knock it out of its orbit. So both the incident photon and the ejected electron are going to be deflected in a new direction as part of the photon's energy is imparted into the electron. So you have a very, very high energy photon coming in, and it's going to smack into an electron, and it's going to knock that electron out of its shell, but then that incident photon is also going to lose some of its energy because it's going to transfer it to that knocked out electron, or the Compton electron, so to speak, and that incident photon is now going to be scattered in a different direction and have a much lower energy than what it started out with. So how much energy is actually lost by that incident photon? Well, I think that actually depends on the amount of energy the photon had to start with. So as far as Compton interactions go, a really high energy photon, whenever it undergoes a Compton interaction, it's actually going to lose a high percentage of its energy to that scattered electron. So the Compton electron, I should say, and that's also sometimes called the recoil electron, just to kind of throw that out there. So it's actually going to impart a lot of its energy to the Compton electron. That's what I'll call it. So the scattered photon is only going to retain a small fraction of its initial energy. But if you start out with a lower energy photon that's going to collide with an electron, only a small fraction of the incident photon energy is going to be transferred to the Compton electron. And the scattered photon is going to be kind of bounced off in a different direction. Obviously as depicted by the picture there, the scattered photon is going to be bounced off in a different direction, but it's going to retain quite a bit of its initial energy. So what does this mean for nuke med imaging? Well, it's actually kind of a little bit of a problem with these scattered photons and our image acquisition. So the radiopharmaceuticals that we like to use, they're low energy emitters, so they're low energy photons, and because the scattered photon has almost the same energy as the primary photon, we're unable to distinguish it with the gamma camera. Whenever you're talking about image acquisition and gamma cameras, you can select for a certain energy window. So if you're wanting to select for 140 keV energy window, and a scattered photon has relatively the same energy as the primary photon, then the gamma camera is going to be unable to distinguish the primary photon from the scattered photon based on their energies. And a large number of those scattered photons are subsequently going to be included in the image. And those scattered photons are undesirable because they increase the background counts and reduce the image contrast. So when we're talking about acquisition, and I know we haven't really gone over this, the radioactive the gamma rays are going to be emitted. As those gamma rays come out of the body, they're going to strike a thallium-doped sodium iodide crystal and knock an electron basically out of its shell, and that excited electron is going to be registered as a spark of light. That spark of light is going to get amplified thousands upon thousands of times, and all of these sparks of light are going to register in these pixels and create an image. So we want only true photons coming out and striking the camera. We don't want these scattered photons because that decreases our image contrast. But whenever you have low energy photons that are interacting with matter, which is the body, we're also going to have these scattered photons. Now, if these scattered photons had a significantly different energy than the incident photon, well, then it wouldn't be a problem because we could select for just the incident energy photon, a very small window. But when you have these scattered photons that have the same energies, or approximately the same energies as the incident photons, then there's no real way for a gamma camera to be able to distinguish between the primary photon and the scattered photon based upon the energy. So then we have a lot more background in our images than what we would actually like. So just while I'm on this slide, excuse me, and we're talking about Compton interactions, I just want to point out that there's three major differences between Compton interaction and like the photoelectric effect. First, Compton interaction involves the photon interacting with a loosely held electron in the outer shell. Remember, that was a distinction before. While the photoelectric effect involves generally a photon interacting with an inner shell electron. Remember, those are going to be much more tightly bound electrons because those are closer to the nucleus. So the very, very, very positively charged nucleus is going to really hold on to those negatively charged electrons that are close to them. Secondly, the incident photon is completely absorbed after the photoelectric effect. And the incident photon after a Compton interaction still exists. It's just scattered in a different direction with a reduced energy. Now, it can be a slightly reduced energy or it can be a significantly reduced energy. It depends on how high of energy the incident photon was to begin with. And third, the photoelectric effect increases strongly with the atomic number of the material, so to speak. So again, Compton interactions mostly occur in materials that have low atomic numbers, so like human tissue. But the photoelectric effect predominates whenever the atomic number of the medium is increased. So the probability for Compton interactions is independent of the medium's atomic number. Okay, so photoelectric effect. Now remember, photoelectric effect occurs when a gamma ray of low energy, or one that's mostly lost, or that's lost most of its energy through Compton interactions, it transfers its remaining energy to an inner shell orbital electron. So this photoelectric effect is going to happen because the photon's going to collide again with that tightly bound inner shell electron. In the photoelectric interaction, the incident photon is completely absorbed by the inner shell electron. Now, some of the energy of the incident photon is expended to liberate that electron from its electron shell. Remember, it has to overcome that electron binding energy. And then some of the energy is carried away by that ejected electron as kinetic energy. And the kinetic energy of the electron is going to be equal to the difference between the energy of the incident photon and the binding energy. So the ejected electron is going to be referred to as a photoelectron. Now what you're left with is a vacancy in that inner shell. So again, what's going to happen with when there's a vacancy in the inner shell? An outer shell electron is going to fill that vacancy in the inner shell, and you're going to have a characteristic X-ray emission. And lastly, for the gamma interactions with matter, we have the pair production, which again, remember, this isn't as important in what we do, but we're just going to talk about it, because it does occur. So remember, for pair production to occur, you're going to have a very, very, very high energy photon, so a very high energy gamma ray, greater than 1.02 MeV, that's going to come close to the atomic nucleus Remember, so it's in that nuclear field that we talked about, and this very high energy photon is going to interact with the electromagnetic fields within and near the nucleus in such a way that all of the energy is going to be converted into the creation of a positron and an electron. So this super high incident photon is going to interact with the electromagnetic field of the nucleus, and it's going to create a 511, or to create these electrons and positrons. So a pair is going to be created. Now the positron produced in the pair that I just talked about is no different from the positron emitted from radioactive decay. So remember we talked about positron emission tomography and positron decay. So this type of positron that we're talking about created in pair production from high energy gamma rays is no different than the type of positron emitted from radioactive decay, from that beta positive decay. So after expending its energy, the positron is going to collide with an electron, and it's going to undergo annihilation. The masses of the positron and electron are going to be converted into two photons, two 511 keV photons. So remember, pair production can only occur if the energy carried by the incident photon is high enough to create a positron and an electron. The masses of the electron at a rest has an energy equivalent to, again, approximately 511 keV. I think that this is basically the same slide that was the previous slide. So just remember again, for pair production, there has to be very, very, very high energy gamma rays. The incident photon has to be greater than 1.02 MeV. So before I told you that gamma rays often interact or can mimic how particles interact. So again, particles would be like alphas and betas, and when you're talking about photon interactions, you're talking about gammas. But regardless, the interaction of electrons and positrons with matter is going to be the same if the photoelectric effect, Compton scatters, and pair productions, the energetic electrons that are set free from the incident photons, these energetic electrons are going to be considered like primary electrons. And the primary electrons are going to travel through matter and lose energy in three processes: ionization, excitation, and bremsstrahlung. And so if you notice under beta interactions, for beta negative interactions, you also notice ionization, excitation, and bremsstrahlung. Also with the positron interactions, and ionization, excitation, bremsstrahlung, and annihilations. So ionization is the process in which an outer orbital electron of an atom is dislodged by a photon or an energetic electron. So again, it can be a photon or an energetic electron. You can think of a beta. This liberated electron pair, the liberated electron of the atom left behind with a positive charge are called the ion pair. So electrons liberated by photons are called primary electrons, while the electrons created by the energetic primary electrons are called secondary electrons. Some of the secondary electrons receive so much energy from the primary electrons that they create additional ionizations all of their own. So that's one of the things that's in nuclear medicine anyway, is something called a dose calibrator. And radiation detection instruments work by measuring the amount of primary and secondary electrons created by the incident photons. So that's kind of how ionizations are used in nuclear medicine. I know a lot of what we talk about, all of you guys are thinking like, well, why do I even care about any of this crap? Like, what is it actually used for in my day-to-day job? Well, that's one of the ways that ionization is utilized in your day-to-day job, because that's the way that well counters and certain types of ionization equipment it recognizes these primary and secondary electrons created by these incident photons. So excitation is a bit different than ionization. Excitation occurs when a primary or secondary electron is unable to knock that orbital electron completely out of its shell, okay? Or completely out of the atom, rather. But it's able to elevate the orbital electron into a higher energy level. So say, for instance, it's able to take an M shell electron and elevate it into an L shell. Okay, so it's going from a lower energy level. So K shell has the lowest, then M shell, then L shell. As you go away from the atom, or I'm sorry, away from the nucleus of the atom, you're going into higher energy shells. Okay? So whenever the incident, or I guess I'll just call it primary or secondary electron, doesn't have enough energy to completely ionize it, so take the electron completely out of the atom, but it's at least able to take that inner shell electron and elevate it to a higher energy level. So the electron in an energy level above normal, its normal ground state, is said to be in an excited state. Okay? Electrons in the excited high energy state are unstable. So when an excited electron returns to its normal energy state, that excess energy is going to be released as light. And certain crystalline materials, such as the thallium-doped sodium iodide crystals in gamma cameras and bismuth germanate and PET scanners, they interact with the incident photons by photoelectric effect and by Compton interactions to create a number of these energetic primary electrons. These primary electrons lose their energy through these collisions with other electrons in the crystal to create additional electrons called secondary electrons. If the primary or secondary electron runs into an electron in the crystal, bumping it up into an excited state, that electron-electron interaction is an example of that excitation. So electrons do not like to stay in a high energy state for very long. It's a very short-term thing. When the excited electron returns to its normal energy state, so it drops back down, the energy it gained from the collision is re-emitted as that light, and that spark of light is recognized by a scintillation radiation detector. That's basically what a gamma camera is, and it works by converting that light produced in the crystal into an electrical signal, which is then processed and amplified to create the pixelated images that we utilize in nuclear medicine. So again, these scintillation detectors are like the backbone of nuke med imaging. So that's what these excited electrons are, and how it's used in general nuclear medicine. Now the last one here is that Bremsstrahlung. So Bremsstrahlung again means the breaking radiation. And Bremsstrahlung is an X-ray created when a fast-moving electron is dragged down by a massively positive charged nucleus. So when an energetic electron passes the nucleus in whatever kind of medium it's traveling through, the really negative charge of the electron is going to be attracted to that really positive charge of the nucleus. Now, because the nucleus is thousands of times more massive than an electron, remember that's where all the mass is pretty much held, the nucleus is going to pull on the electron by causing an electrostatic attraction. And the forces of the electron it forces the electron to deviate from its original direction. Sorry, I had to get another drink. Oh my God, this thing's already over an hour long. I've been talking forever. But where was I? Okay, so this negative charged electron is going to be attracted to the very, very positive charged nucleus. And what's going to happen is it's going to cause the electron to change from its original direction, and also it's going to slow down and lose some of its energy due to the pull on the nucleus. Okay, so the energy lost by the electron is emitted as an X-ray, and the X-ray, it's called an X-ray as opposed to a gamma ray because the X-ray originated again from outside of the nucleus. So that's the main difference between gamma rays and X-rays, is gamma rays originate inside the nucleus, X-rays originate outside of the nucleus. And the term Bremsstrahlung, or breaking radiation, is just descriptive of the X-rays generated in the process. The kinetic, think about like if you you can think about it like like when you're driving and you apply brakes to slow down a really fast moving car. Okay, so if an electron, a high-speed electron, is coming in close to the nucleus, it's basically like it puts on the brakes, so it slows it down. And that kinetic energy of the moving electron is changed to X-rays when it's slowed down by that nucleus. And lastly, annihilation. So again, for annihilation, it's basically the opposites attract sort of thing. So positively and negatively charged electrons, so positrons and negatrons basically, are antiparticles of one another. So when positrons are produced during radioactive decay, so during beta positive or positron decay, and are ejected from an atom, they have enough kinetic energy to just travel a few millimeters. Okay, so they're going to zigzag a couple of millimeters. They're not going to go far. And then that positron and an orbital electron from an atom are going to be attracted to one another through those opposite charges. So this opposites attract sort of effect is going to cause them to collide together and interact and produce an annihilation. Now, the path distance required for the positron to find an electron for this type of annihilation interaction depends on the positron energy and the number of electrons in the immediate area of the atom from which the positron was originally emitted. So in the annihilation process, the mass of the two particles is converted into an energy. And remember that Einstein's equation from, I think it was your first PowerPoint, the E equals mc squared. The rest masses of the positron and the negatron are identical. They're both 511 keV, so having a total energy of 1.022 MeV. The detection of the two annihilation gamma rays, again, is the foundation of positron emission tomography. Oh, well, I guess I kind of went over this already on your previous slide, but I'll just kind of briefly review what this slide says anyway. So again, ionization is a charged particle can transfer enough energy to an electron, usually an outer shell electron, to eject it completely from the atom. So it knocks that electron completely out. Okay, the ejected electron, again, which has a negative charge, and the atom's left with a positive, and the atom left, so that would then have a positive charge, are considered an ion pair. So if an incident photon knocks an electron out of the atom completely, then the positive atom and the ejected electron would be considered that ion pair. So the primary electron is going to be the electron that's actually ejected from the atom by the photon. Secondary electrons are created from that primary ejected electron. So the secondary electrons are still really energetic, and they may cause additional ionization. So those secondary electrons may have enough energy that then they can knock another electron out of completely out of an atom. So again, the dose calibrators and survey meters work by measuring the amount of primary and secondary electrons created by incident photons. That's one way that ionization is actually used in general nuclear medicine. Okay? So when you talk about ionization, you can also talk about specific ionization. So for specific ionization, the linear rate of energy attenuated by the linear rate of energy attenuation of the ionizing radiation is measured in terms of the number of ion pairs produced per unit distance traveled. So remember, and the ion pair is that ejected electron and then the positively charged atom. Okay, so that's the ion pair. So radiation that is caused by the ejection of an atom of an absorbing material, which results in the positively charged atom, and that free negatively charged electron is the ion pair. The amount of energy transferred per ion pair created, that's what's referred to as W, is characteristic of the absorbing material. The number of ion pairs created per unit of distance per unit of distance the radiation travels is referred to as specific ionization. Okay, so an alpha particle has a very high specific ionization, okay, in the order of thousands of ion pairs per centimeter of air. So remember, alpha particles have a very, very high energy, right? And they travel 2 to 6 centimeters in air. So, and that's just in air. So remember, if it's in tissue, it's only going to traverse a couple of cell depths. So it doesn't go very far at all. But in air, it's going to travel only a couple of centimeters. Okay, and the energy from an alpha particle is so high, it's going to be able to create lots and lots and lots of ionizations. Okay, so it's going to be able to knock a whole bunch of electrons out of shells of several different atoms. Okay, so it's going to have a very, very high amount of ionizations that occur in a very, very short distance. Okay, so that means it's going to have a very high specific ionization. Now, when you're talking about alphas, you can also talk about linear energy transfer. So for linear energy transfer, it's the amount of energy transferred in a given distance by a particle moving through an absorber. Okay, so linear energy transfer is related, obviously, to specific ionization. I think the equation is linear energy transfer is equal to specific ionizations times the W. Okay, so alpha particles are classified as having a very, very high linear energy transfer, and that makes sense, right? Since alpha particles have a very high specific ionization, they create lots and lots and lots of those ionization pairs, but they travel a very, very short distance, so they're going to drop all of their energy over this very short path. Okay, think about something as like a gamma that travels forever far distances. It doesn't have a whole lot of energy, so it's not going to necessarily create a lot of these ionization pairs, and of the ionization pairs that it creates, they're going to be spread out over this huge distance, so they're going to have a very low energy transfer. So now we're going to talk about the penetrating ability of radiation and basically like a health hazard. So generally speaking, if you're talking about penetrating radiation, it's generally used to describe X-rays and gamma rays, because those are the ones that have the potential to generate or to penetrate considerable thicknesses in material. If you refer to, I don't remember which slide it was on, alphas aren't very penetrating. Remember, they can be stopped by like a really thick sheet of paper, and betas can be stopped by things like pieces of wood or concrete, and gammas can keep going. They have to be stopped by something like lead. So they're very, very penetrating. Okay, they may not be very high energy, but they are very, very penetrating, meaning they're going to travel very far. So an individual photon can travel several centimeters or farther, even in tissue, before it interacts. So in contrast, like charged particles like alphas and betas, they undergo very many closely spaced interactions, okay? So it limits their penetration ability. So remember, alpha particles are going to have the highest amount of energy, but since they travel the least amount, the smallest distance, they're going to be the least penetrating of the basic types of ionizing radiation. So remember, they don't penetrate the skin, and they can be stopped by that thin piece of paper or clothing. You know, that doesn't mean that they don't pose a health hazard, though. I mean, a health hazard could occur with with alpha emitting materials if they're inhaled, swallowed, or they enter the body through a wound. So they're pretty much considered like an internal health hazard. And they're really only used in nuclear medicine as far as bone cancer treatment. Now, beta particles, they travel 100 times the distance of alpha particles in air. That still doesn't mean that they travel, like really, really far. They're kind of more, I guess if you have to think about it as the intermediary between a gamma and an alpha. But they are able to penetrate the skin and the tissue, and you have to have like a little bit of aluminum to be able to stop them. So beta particles can technically be an internal and an external health hazard because they do penetrate the skin and the tissue. Now, gamma rays are the most penetrating type of radiation, and they can travel several meters through air and many centimeters in the tissue. So because gamma rays can travel through the body, they're sometimes referred to as the penetrating radiation. Okay, so they can constitute an internal and an external health hazard technically. And again, I think I already covered this whenever a few slides back, but just to kind of review it. So excitation, again, is kind of the backbone of nuclear medicine imaging. Okay, so I'll try to always bring it back to why it's important for you to know this. So primary and secondary electrons that don't have enough energy to actually cause ionization, so they can't eject electrons from the atom, they can transfer some of their energy to an electron and bump it into the next energy shell. Okay, so whenever that electron, it doesn't like to be in that excited or that higher energy state. It's not going to stay there for very long. It's going to fall back down, so it's going to be de-excitation. Okay, so it's going to return to its ground state, its normal state, and it's going to release that excess energy as a photon of light. And that little spark of light is going to be registered, like I said, like by the thallium doped sodium iodide crystal. It's going to be registered as a spark of light, and that scintillation event is going to be amplified through the computer processing software of scintillation cameras like gamma cameras and PET scanners, and that's what's actually going to create the counts and the pixels for the images that we acquire. And then again, with the Bremsstrahlung radiation, I don't know that I actually talked about why BRIMS is not necessarily considered a good thing in general nuclear medicine. So for beta particles, as they pass through materials, they can produce these, again, secondary radiations that are called Bremsstrahlung or breaking radiation. The probability that this will happen is greatest when high energy betas and high atomic number materials such as lead. That's why plexiglass, not lead, is recommended when working with high energy beta emitters like P32. And that's also why in Nuke Med we don't wear lead shielding. Right? So whenever you think about like an X-ray tech, they actually have to wear lead shielding, but we don't wear lead shielding due to these Bremsstrahlung radiations that increase with the high atomic number materials such as lead. So again, BRIMS are generated by fast-moving electrons from beta particles, and that's normal beta particles and positrons, okay, so beta plus and beta minus, and they're released from a decaying nucleus. So the high-speed free electrons interact with the matter by slowing down as it travels near that nuclear force. The amount of energy released is going to depend on how close the electron gets to the nucleus. And it's going to produce this very broad spectrum of photon energies. So whenever you're talking about if I asked you a question about beta emissions and the photon energies, and why there's a broad spectrum of energies versus a discrete energies, it would be from this breaking radiation, this Bremsstrahlung radiation, because the energy that's released is going to be dependent upon how close it gets to that nucleus and how many protons are actually in that nucleus also. And if I asked you which types of radiation generate Bremsstrahlung radiation, I would hope that you would answer, beta radiation and positron, because remember, positrons are betas also, right? They're beta positives. So annihilation only occurs with positron. So other things that we were talking about, like ionization, excitation, and Brems, those all occur with both positron and normal beta decay, okay? But annihilation only occurs with positrons, so only beta positive. And so remember that annihilation is that reaction between a pair of particles that results in their disintegration and the production of an equivalent amount of energy in the form of photons. So remember, the incident positron is going to collide with an electron, basically, and it's going to give off two 511 keV photons. So we've talked about the interaction of radiation with matter, and kind of what happens with the energy as it's moving through different types of matter. So when you're dealing with radiation protection, what you're mainly interested in is estimating how much of a given amount of shielding material reduces the intensity of the radiation from the source of that radiation. So for example, if we take a radioactive material and we put it inside of a lead container, the radiation intensity, if we measure it, it's going to be reduced, okay? So that's basically what you would think of as the atomic and the subatomic levels. You can think of that reduction in the radiation emitted, or at least the reduction in the radiation detection, is going to be due to the absorption in the lead container due to, like, the photoelectric effect, Compton interactions, ionizations, and excitations. But you also have to think about attenuation. So attenuation occurs in two basic ways. First is by absorption of the photons in an absorber. Okay, so this is called absorption attenuation. And the second is by deflecting the photons by atoms in the absorber away from the point of concern, and this is called scatter attenuation. So attenuation is a combination of absorption and scattering. Scatter attenuation is due to the Compton scatters. Absorption attenuation is due to the photoelectric effect. So shielding for beta particles is pretty easy, actually, in real life. So whenever you're injecting a radioactive isotope, you have like tungsten shields that you put over your doses to limit the amount of radiation exposure that you're getting to your hands, or you draw doses behind lead shields, lead L blocks, or you carry your doses in lead toolboxes, as we like to call them. So there's different types of ways that we can attenuate that material so that we're decreasing our radiation exposure, because we work with this stuff all the time. So when you're talking about attenuation, you have to talk about the attenuator, basically the material that's going to cause the loss of the photons, or the attenuation. Okay, so it's the amount So for different attenuators, you're going to have what's called a linear attenuation coefficient. Okay, so that's a property of the attenuating material, or the attenuator. Okay, so it's usually a thickness given in centimeters, or is expressed as a thickness in centimeters, and it's dependent upon the energy of the photon, the average atomic number, and the thickness of the attenuator. Okay, so when you're talking about matter that's capable of lessening the intensity of the photons, then you need to talk about the attenuator material and what properties it has to be able to stop that penetrating ability. So the linear attenuation coefficient is greater for dense tissue such as bone than it is for soft tissue. Okay, so the thickness of that attenuator, the density of the attenuator, so the attenuation coefficient would be greater. So in general, the linear attenuation coefficient, again, it's going to depend on not just the energy of the photons, but and on the average atomic number, so the Z number, but on the thickness of the attenuator. The lower the energy of the photons, or the greater the average atomic number or thickness of the attenuator, the greater the attenuation. So the mass attenuation coefficient is the linear attenuation coefficient divided by the density of the attenuator. When the density of the material is given in grams per cubic centimeters, the units of the mass attenuation coefficient are going to be in centimeters squared per gram. So half value layer you can think of as stopping power. So half value layers and 10th value layers, basically it's a material's effectiveness as a photon attenuator. So a material's effectiveness as a photon attenuator is described by the attenuation coefficient. That's basically what an attenuation coefficient is how capable is it of stopping those photons. An alternative way of describing that would be talking about half value layers, which is simply the thickness of a slab of the attenuator that removes exactly 1/2 of the radiation of a beam. Okay, so it's the thickness of the attenuator that reduces the intensity, so the number of photons in a beam, by 50%. And of course, 10th value layer would be the thickness of the attenuator that reduces the intensity or the number of photons in a beam by 90%. So it's important to remember that each material has its own specific half value thickness, okay? A material, so it's energy and material dependent. That means that for any given material, if the radiation energy changes, the point at which the intensity decreases by half of its original value is also going to change.